My name is Hernán Rivas Acosta. I work at Inaca, part of Erlang Solutions. And I started out as a game developer like a few years ago. And I discovered Erlang to make a multiplayer server for a game. And since then, I loved it. And I was really, really lucky to get into Inaca and be able to work in Erlang full time. So today's talk is about making a reliable reporting system with Kafka. But it's also about how did I actually design Kafkerl and what lessons we can take from that, particularly on how to build a library more than anything else. So first of all, we started out by choosing what were the right tools for the shove. And this was a system we built for TigerText, a messaging application that has quite a few requirements. In particular, it's HIPAA. The HIPAA requirements, like the secrecy and the audits for medical applications. So we not only have a lot of services and different processes generating reports all the time, we need to make sure those messages are not lost. And also we have an unknown number of simultaneous systems reading from the feed of logs, not to generate an error log or to see what went wrong, but to see what exactly happened. So for example, this person joined and now is talking to this other person and it's sending these messages, because all this is part of the rules that HIPAA imposes on us. Also having, for example, the order is preferred. This is because we are trying to make a lot of what happened to make for any audits that may be required later on by the hospital. And we're also using it for the statistics. So losing things in general is a better idea. And we looked at the options, and we found quite a few. Of course, we picked Kafka, but RabbitMQ is a great choice, ZeroMQ, Flume, they're all great choices, but we chose Kafka and for a few reasons. So the main focus of Kafka is high throughput and low latency. And this was very appealing to us because those were two things we were going to have. High throughput because we were generating a few logs for every message that is sent on this messaging application, things like Skype for doctors. And it was also used by LinkedIn, Uber, Netflix, among others. Those are the most famous ones. So we knew that if it handles whatever volume LinkedIn can throw at it, then we are just safe. We're good to go. Also, the redundancies are great because, again, we are forced to have a bunch of redundancies. And our data engineering team comes from LinkedIn, so it was an obvious choice for us. However, there are things that make Kafka special. There are things that are kind of specific to Kafka that were really good for us. The distributed architecture, not exclusive to Kafka, but the way it works is pretty interesting, using, topic and partitions. A topic is like a feed of records. When you send a log, you just say this belongs to a topic, and then you go and another process goes and reads from a single topic and gets the list of messages. Partitions are usually not used semantically, but you can basically are like subtopics. Inside a topic, you have multiple partitions, and you can write to any partition. You give it the meaning you want. It doesn't have any off the box. And it also has a replication factor that is highly tied to the topic. So if you have a replication factor of 3, you know that every topic partition pair is going to be at least, actually exactly on, but technically at least, 3 different brokers, 3 different computers. If at least one of those is alive, then you can consume from it. So you're not losing information. If you use a high replication factor, you can be pretty you can offer the guarantee that you will not lose anything. And also the performance. Another cool thing about having this distributed is that there are a bunch of brokers. Think of a broker just as a server, any normal server running Kafka. And each one of those is the leader of certain partition and topics. The leader means that if you want to consume that, then you have to go to it. So the performance it comes from the fact that it's parallelized. It's well distributed among the different nodes. So we had to implement, we had to use this on our side. It has a binary protocol, and we needed a library. And there were quite a few options. We Googled a bit, but keep in mind, our focus was to support the features that made us choose Kafka. That is the way it handles the throughput by using multiple brokers, for example. So it had to be well distributed in the library too. And we found multiple choices. Well, this is basically a summary of what we were looking for, but I mentioned it. And there's the libraries that we found were, well, first of all, I found this from Wooga. Wooga is a gaming company. I know them from back in the day when I did video games. They were the company I cited when I wanted to use Erlang for a server. So great company, I know them. The protocol is tested, but it has a problem where it buffers the entire response. Basically, when you request the logs to Kafka, you don't get a huge binary. You get multiple small ones. And where Kafka decides to cut them is up to Kafka, and it's unpredictable, and there is nothing you can do about it. One thing that you can do, Kafka Erlang from Wooga does it, is you buffer the entire response and then parse it, and it's easy to parse that way. However, that means that if you're getting a bunch of logs, it's going to chew up a big chunk of RAM, and you usually can't afford that on your live systems. And also, it doesn't offer support for the latest version of Kafka, 0.8, so that was pretty much out. The next one I found was Broad by Klarna. Broad is a nice name. It's Kafka's biographer. The protocol is again tested. It's very well documented, but it has two problems. First of all, it does the same thing I mentioned before of buffering the entire response. And then it serializes every message through a Shen server. And what I mean by this is that when you send a message to Kafka, there is, I don't remember the name, but broad.erl. It has a Shen server, and every message goes through it, and it gets into the message queue, and then it builds the binaries and sends them to Kafka. This means that you have a single process that's basically not exactly a single point of failure. I mean, it could be if that process crashes and it has a large message queue, that's all gone forever. But the other problem is that it's a bottleneck. It's a performance bottleneck. Like you have all this fantastic distributed architecture, and you're bottlenecking on your application. And finally, we found eCaf, which has excellent documentation. The other ones have good documentation, but this is excellent. It's being maintained. The code is really easy to read. It uses an FSM to handle the different states of when it's connected to Kafka and when it's expecting responses from Kafka. That's a really clever solution to the problem. Super easy to read because it also has comments everywhere. It's a fantastic code. But it has the same issues as before, like the bottlenecking, not through a Shen server, but through a Shen FSM. And it has no consumer, which was a bummer because we could have started adding small details, but we found out it was maybe easier to just go for it ourselves. So, well, we started building Kafkerl. And it has a bunch of things. I try to do basically everything that was implemented in Kafka. So trying to use better bandwidth. Kafka allows you to bundle a bunch of messages together. We do that. We cache the messages. It's concurrent. I will talk about this later. We don't lose the messages. We use backups. Before sending them, we back them up. And when we get a confirmation that they were delivered, then that's when we can safely discard that backup. I also had the idea of making a simple API using the same words that the Kafka documentation has. What I mean by this is like the concept of consumers, producers, and all that stuff. That's the names I have for the API. That means that you should probably, if you know Kafka, you probably already know how to use this library. And how? How exactly did I implement these things? Well, we avoided serialization by using ETS tables. I'll have a few slides explaining this more depth, but basically there are a bunch of ETS tables where everyone that wants to log something writes to. And this gives us as much concurrency as Kafka, because we have an ETS table for each topic and partition. And since Kafka uses the topic and partitions to provide concurrency, we are doing the same thing. And we have the same amount of concurrency that Kafka has. So for example, if you say, OK, Kafka is being overloaded, we need more, like we need to increase the amount of partitions in topics, then Kafkerl will reflect this instantly, because it will spawn more ETS tables. So you will have the same solution to the same problem on both sides. Also, the message parsing, well, I handle partial responses basically by saving the part of the binary I couldn't parse. I parse until I can't, until it fails, and then I save the extra binary, and when the next binary from TCP comes, I just put in the start and try to parse it again and again until I finally have the last answer. There's fault tolerance built in, basically using the ETS, as I mentioned before receiving confirmation. And also the ETS, all of them are supervised separately. Like that's a very basic scheme of how it works. Separately, so I separate the messages from all the processes, meaning that if a process goes down, there is nothing that goes down with it. Like the messages are not stored there. So we don't care about the message queues of those processes. Also, if the ETS becomes too big, because that could happen, for example, if we're trying to send to Kafka and Kafka is down, then our ETS will start to buffer the messages that didn't get confirmation yet. So if that gets too big, we dump them all to disk. Yes, that causes us to lose order, but we're talking about like a service outage, so, well, nothing we can do about it. Also, this architecture allows us to handle the broker changes. Kafka can do that whenever it wants. For example, if a broker falls down, it will redistribute the load or start up more instances. All that is handled automatically because, again, the processes that are connected through ChainTCP to Kafka don't really matter. If I remove them all, I haven't lost any messages. So there's like no special handling that I need to do. I just took them all down, put them all up. And finally, I don't let it crash. This is like an extra thing. I know it's usually a good idea. And in fact, there are a few places in Kafkerl where, yeah, letting it crash is a smart thing. For example, if a broker connection fails, I don't care. But what I mean by this is don't let it crash unless you have to. And if you have to, you need to have a way to restart the whole thing. So for example, a broker falls, yes, the process may crash, though as far as I know, they don't. I haven't seen a single log that they say they don't, because all the different responses I try to handle, and I kill them by hand if I think it's a good idea. Again, we need to make sure we are not losing messages. So any step we can take to minimize that risk is a good thing. And how do the ETS work and how they provide concurrency? Basically, how I'm using this to do what I mentioned before, mimicking Kafka's architecture on the Erlang side. So first of all, we have like Kafkerl, the library, and Mr. Kafka on the right, the writer. And you request a metadata. And the metadata has a bunch of information, but mostly we care about how many topics we have, including the names of the topics and all the stuff, and how many brokers we have. Also, there is a mapping, but it's like implied. There is a mapping there which brokers handle which partitions and topics. So first of all, what we do, we create one ETS table for each topic partition. In this case, we have 3 because that's what fits in the slides, but we have like a few dozens on the production server. And we also create a broker connection, that's a process, for each broker on Kafka. That just has a ChainTCP connection and does a very small pieces of logic regarding when to talk to Kafka. So we receive a message from any process. It goes to the right ETS, and it's written there. And the cool thing about this is that the process creating the log, the message, that's the one that writes to the ETS. So everything to the right of the orange boxes, that's untouched. That doesn't have any performance impact, no matter how many messages you receive. They all get routed at the same time. ETS allows for concurrent writes internally. And I also use a library from Shay Nelson. Yeah, you're over there. So I use concurrency controls that simplifies a bit, because the API for ETS is, well, could use some love. Well, he did it, and it's way better that way. But again, the most important thing is this is extremely concurrent. All the messages are routed by the process generating them. So the concurrency is equal to the amount of topics or ETS tables that Kafka has. Again, the same strengths and perhaps the same weaknesses. So what happens later is that the broker connections themselves choose to send information to Kafka. How they do this? Well, there are two ways. Either time, they try to send a message every few seconds, like 30 seconds. Or when the ETS tables have too many messages, they can try to send multiple ones. The only thing that blocks them is that until I get confirmation from Kafka, I don't try to send them, because I don't want to overload the backup ETS that each broker has, the one that waits for the messages until they are confirmed. So basically, this broker decides for whatever reason to send to Kafka. So what it does is it picks up whatever ETS tables it's tied to. And this is the same that happens on the Kafka side. So in this case, Kafka would have two brokers with 3 topic partitions. And one of those brokers is going to handle two different topic partitions. So it's, again, the same architecture on the other side. And we can see messages arriving on the left side. And it doesn't affect anything that happens to the right of the ETS tables. So this builds the binary. I skip the part where I do the backup thing on another ETS table. And it sends the binary to Kafka. There's also the whole thing with compressing. Kafka accepts compression on those messages. So you have a binary, and since it's mostly text and a few repeating headers, that compresses really nicely. So you can compress it. Another extra advantage of this is that it compresses all the data, and Kafka can write the compressed data. So it saves that to disk directly. It's really clever how it works on that side. And what we see here is a leadership change. This is something that Kafka decides for whatever reason. Maybe a broker went down, or maybe we changed a replication factor, like in this case. So what I do is, again, as you can see, the left side, messages keep coming in. And we remove the brokers, the broker connections through TCP. This is just killing them, and spawn new ones. And these all have their own timers, and they keep working like before. So the system, at no point between sending messages, between changing leadership, at no point had a downtime. And that's basically, in summary, what's going on. The messages were never serialized through a single process or multiple processes. We can write concurrently to ETS tables. We cannot crash a process and lose messages, because this is not reliant on the state of a Gen server or the message queue of a Gen server or any process for that matter. And also we have the simultaneous reads and write. And a better summary would be to say that we have no downtime, no missing messages, no special cases, and no errors, because we know we separated all the messages that we don't want to lose from the rest of the system, and we don't really care if it goes down or not at a certain level. And that brings me to what I consider good design. And by good design, I mean that if we chose Kafka, which we did that for a reason. We did that because we like the architecture. We like the solutions it proposed to the problems. So why would we reinvent the wheel when we're doing the API? If we try to mimic what we did, what Kafka did, then we're going to arrive to the same advantages that Kafka has that we liked. And also there's also the simplicity on naming methods. that we try to name the methods in the same way Kafka does, and the simple data types, because Kafka is written in Scala, and if you're going to be honest about it, it only uses binaries and integers for the partitions and binaries for everything else. So we use only that data. We do use tuples, but that's just to wrap the message inside. So it's a very simple data type that anyone could, again, pick up if they know Kafka. And that's kind of the point. Like, this is an example of the API. We have, there are a few more functions, but basically we have produce, overload, consume, and request metadata. There are a few more, like stop consuming is depending on if you want to consume actively or not, like if you want to keep polling automatically for new messages. But all in all, the API is super simple. And if you ever use Kafka, you will be familiar with those terms because those are taken directly from Kafka's documentation. And also, another small detail regarding this is that we use very strict data types. Again, with the whole binaries and integers, but more to the point, we could use IO lists to send the messages. Like, the messages could be IO lists. But if we did that, we would have to make sure that there are no errors anywhere else. Right now, when you send a message, I know it's a binary. So I know there won't be any surprises. If it's an IO list, maybe you send a tuple inside or an atom, and that will crash when we're trying to package the messages. And how do I fix that? Well, if the broker were to crash while sending the message, then it will simply retry and crash again, and retry and crash again, and eventually the supervisor will crash and die, and it will bring the entire system down. So to make sure that never happens, we are very strict on what we accept, so that any errors will be caught early on, and we have no surprises or edge cases, particularly sending IO lists that are just actually lists. And that's an example of what the simple API looks like. We just have the topic partition. Those are binary and integer. Same with the payload. It's a binary. Nothing too strange, nothing weird to accept there. And all in all, this is the objective was to use a facade pattern too. Meaning we have an easy to understand API. It's all in the same module, like the rest of the complexity is hidden away. And it's super simple to use. That was one of our points, because we have a lot of developers, and we can't afford to just have people learning this new library. And in case I had to change anything, learn everything again. So the last point is testing. And Kafka has this thing that is kind of hard to test. Why is that? Because, well, and why is that? Well, Kafka is a service that it's not written in Erlang, it's outside Erlang. So how do you test it? You can test it by, for example, mimicking the responses that Kafka gives you on Erlang. Broad, the library I mentioned before, it does exactly that. It has like a fake Kafka inside, and it uses us for the tests. But that's only changing the problem, because if your replica of Kafka is not exactly the same, you will find troubles later on. So first thing we did, dialyzer. And I would recommend this for everyone all the time on everything. But dialyzer is really good. It tests your API. And one thing I found later is that when you go and change things, like sometimes you make architectural decisions and you regret them and go back, well, that leaves traces. It leaves garbage. It leaves functions that you're no longer calling and you forgot to remove. Well, dialyzer is fantastic for that. It tells you this function is not being called, or the arity of this function is not what you expect. And basically, it's a sanity check. It calls everything that should be caught by a very clever developer that I am not. We also have unit testing. This is the testing that I noticed most of the other libraries had. Basically, the protocol can be tested, the ETS tables in your implementation, and basic functionality, all those can have their own unit tests. But still, an integration test is is something else. And proper can actually help you in that regard a bit, because you can use proper to generate weird data and then connect to an actual Kafka server running on your own machine and see what happens. But that's not exactly like a nice integration test, because again, Kafka can reply different things and for certain conditions that you have no control over. So you would have to make a fantastic suite that kills brokers on your machine and sets them up and changes things through Zookeeper. So all that would be extremely complicated. So my point, it's live, just send them. I mean, if it works, if your library works, then put it on staging. And that's one lesson that I liked. It worked from pretty early on. And I put it on staging as soon as possible. And what that gave us is, so in our staging environment, we have a bunch of testers testing the application themselves and the features that we have. So they generate Kafka reports basically by just doing their jobs. And there were a bunch of errors that we caught that way. And a lot of the answers that Kafka gave us, let me give an example. So sometimes Kafka will confirm the messages you sent altogether, except when it doesn't. And when it doesn't, it's rare. It's really rare that it does it, but it's something I never noticed that could happen, because on my local test, it wasn't an issue. However, on staging, eventually, it did. For once, it gave me an answer I couldn't. So I had, like for any unexpected answer, I logged it, and I went back to the design board, and I had to fix that. So maybe I get like confirmation of delivery of half the messages, because again, it's related to the fact that brokers have multiple topics, and maybe one topic wrote correctly and the other one didn't. But the point is, it happens, and it's something unexpected, and it's something that I wouldn't have found out without putting on staging. And well, this also meant that after the staging part concluded, and we said, OK, it's not failing anymore, we felt confident enough to just put it in production, because we knew that at worst, the worst case scenario, if it crashes, we lost some logs that we didn't have anyway, because we had no logging system. So put it in production too was a good idea. The staging part made sure that we wouldn't broke anything else. So the question is, how did it go when we put it in production? Well, it went really well for like, 8 months, I think. 7.5 months, 8. And then, eventually it had to happen. It completely died on me. So there was a downtime. There was a downtime on the Kafka side, an upgrade to Kafka, a new version 0.8.2, I think. Well, that didn't go so well, and that didn't work so well. So whatever. As I mentioned before, we do save to disk if the ETS gets too large. So whatever, right? Just go get the logs. And where were they again? They were supposed to be there somewhere. No, we didn't have permission to write. That's something that you cannot account for. Never gave permission to write to random directories. And for the sake of the argument, this was a random directory that Kafkerl was trying to write to. So it crashed. And we lost those messages, and it was a real shame in production. But then again, it did last 8 months. And well, that's the nice note where I'll finish this, that eventually the whole replicating the system, the Kafka architecture, meant that we didn't have any performance problems that are exclusive to the library. Like any performance problems would have been in Kafka first and then in ours. And also the whole put it on staging as soon as possible really paid off. And well, that's basically it. And if you have any questions.
So can you elaborate a little bit about how you organize your messages in the ETS? I mean, I assume that you're just storing things there and you keep some ordering or some sort. And how is that structured?
OK, so the question is about how are the messages stored in the ETS. Well, the library I mentioned that Shay wrote, concurrency controls, have multiple abstractions on top of ETS. And one of them is like basically a buffer that writes the messages in order. So we use that. Frankly, I didn't write that part, but it works pretty well. But yeah, that means that it's guaranteed the order. Whichever process got to write on that slot, so it reserves a bunch of slots in the ETS, and it gives permission to write to those slots to different processes. So as soon as one says, I want to write, it gives that slot to the process on the back. Jay's about around there, so you can ask him specifically how it works, but we rely on that tool. Otherwise, what we would have to do is to, try to implement something similar ourselves, but that may have problems on the ordering. The ordering may not be what we expect, because you want to write to the ETS, and it's basically like appending to a list, and maybe you lose the order in there. There are a few details that may go wrong. If the write fails, then it will go after whatever writes came before. However, that other solution that I mentioned from Jay, well, that takes care of it on the background.
What happens if the VM crashes?
Yeah, if the VM crashes, you're done. You do lose the messages. Well.
More questions? So what kind of scale you guys are pushing?
Oh, we have, I don't remember the number, but around 20 million messages to Kafka a day. I don't know what that is, about an hour. Because we have multiple for every message we send, and I think this is also indirectly used by Whisper, that they have a higher volume that I'm unaware of.
So 20 million a day?
Yeah. 20 million like Kafka writes a day.
Do you know if that's bursty or smooth?
Usually kind of smooth. We don't have too many bursts, because the worst that could happen, so we create logs when you create an account, when you join a group, when you start a conversation, and unless multiple of those things happen at the same time, it's not. We only have bursts when, so this, as I mentioned before, this is for hospitals and doctors. And the burst may happen if a hospital decides to, join 10 more doctors, or 100, or maybe an entire organization joins. So then you will have a record of everything that happened, like the organization is created and every account is added and all that generates records. But that's rare. We usually have a smooth, nice amount of messages all the time. But the burst never never caused any issues. Sorry?
Consuming from Kafka?
Oh, yeah, so about how the flow works from consuming from Kafka. That's kind of different. So Kafka comes with something called consumer, console consumer, which is basically a small, I think, Python app. And we did basically the same they do. So you connect to any Kafka server, and they all have the leadership. And you get what broker you try to consume to, you connect, and you read the messages as they come. There is no magic with ETS involved in that case, because you can only consume from one topic at a time. If you want to consume from, one topic partition at a time. If you want to consume multiple ones, then you need to spawn multiple processes, because you need to connect through different TCP connections to even the same broker. Because every broker has so it knows where you are consuming from per TCP connection. So if you want to consume 2 topics, you need 2 TCP connections to different ports, because that's how it identifies who you are.
Then is your library keeping track of the log segment and byte offsets, or is that managed elsewhere?
So he's asking who keeps track of where you're reading. Yeah. So both, kind of. While you are consuming, the library takes care of it, and then it will say, okay, I'm consuming from this top, so it gives you a bunch of messages and say, okay, all these messages come from this topic, and you're on this offset. Now, if you keep consuming from it, yes, the offset will stay on the process that handles it, on Kafkerl. But if you, for whatever reason, stop consuming that and start consuming again, you will have to remember where you were when you stopped.
Okay. Thank you.
Thank you very much.